The last section on equilibrium involves Le Chatelier's principle. Le Chatelier's principle states that when a system is at equilibrium and it's placed under stress, the system will undergo a change in such a way as to relieve that stress. In other words, the system temporarily shifts in order to re-achieve equilibrium. Now, there are many different kinds of stresses that can be put on a system. One of those stresses is temperature change. So if you had a closed container of ice and water at equilibrium, and then you were to raise the temperature, what you're actually doing is feeding energy to the ice, essentially, and that energy will cause the ice to melt, and so you will get a temporary shift to the right in order to restore equilibrium. So it's almost as if it's, trying to use up what you've put in there. So the system will temporarily shift to the right to restore equilibrium. So energy is one change that can be made on a system. If the energy, by the way, were on the right side of the reaction and you added energy, that would cause a shift towards the left side. If you were to remove energy from the reaction that you see on the screen, then the reaction would shift to the left in order to restore or sort of replace that energy that has been removed. So kind of think of it as it's trying to balance out whatever that stress was that was put on it. Now, a second change that can be imparted to a reaction to cause a stress is concentration. So if you had a closed container of N2O4 and NO2 and the system is at equilibrium, and then you dumped in a bunch of NO2 to the container, you're going to have lots of NO2 with the potential to react. And so this reaction will have a temporary shift to the left to restore equilibrium. So you've increased the amount of NO2, so there's more NO2 that's able to react. So temporarily you're going to get a shift to the left, producing a lot of N2O4, and then eventually you'll reach that state of equilibrium once again. Now, during this process too, with some reactions, when there's a shift, you may actually notice a color change depending on the colors of the products and the reactants. So if there's a temporary shift in one direction, in this case to the N2O4, the color of the N2O4 then will become the predominant color in the container. Now, obviously, if there's no color, if the substances don't have any color, you're not going to necessarily see a color change. Now, the third kind of change you can impart is to actually remove or decrease the concentration of one of the reactants or products in the system. So here's an equation representing water gaining energy and turning into a vapor. Now, if you were to remove some vapor from this system, what's going to happen is the water and the energy essentially are going to come together, and you're going to get more vapor produced, almost as if you're replacing the vapor that has been removed. So you'll actually get a temporary shift to the right in this particular reaction. So again, we can change energy, we can increase the concentration, we can decrease the concentration, and then finally the last change that can occur is a pressure change, and this is mainly with gaseous systems. If we had a closed container of N2O4 and NO2 and it's at equilibrium, and then we increase the pressure, anytime you have an increase in pressure, that indicates that you have decreased the volume. When you decrease the volume, the reaction generally goes in the direction producing the least number of moles. So in this particular case, that's going to be a shift to the left. So again, when you increase pressure, you're making the volume of the container smaller, so the reaction's going to shift in the direction producing the least number of moles, which would be a temporary shift to the left. Now the opposite would occur if you decreased pressure, and so you had a larger volume, then the reaction is going to shift in the direction producing the greatest number of moles. Now, if the moles are equal on both sides, you look at the coefficients and there's 2 moles on one side and 2 moles on the other side, and you change the pressure, increase or decrease, you will see no change in the system. There will be no shift at all. So in this particular case, the system temporarily shifts to the left in order to restore equilibrium because there are fewer moles of gas on that side of the equation. And one more time, if the moles happen to be equal on both sides, if it was a chemical equation that when you balanced it, you had the same number of moles on one side as you did on the other, then a change in pressure would result in no shift at all in the reaction.